Now, as we go forward trying to find maximum and minimum points of our function, or maximum and minimum values of our function, the good news is that it's just totally like what you already know from single variable calculus. We're going to look for the critical points and using the first derivative, and then we're going to classify those critical points using the second derivative, and that's it. So now these tests are adjusted a little bit because we've got more variables flying around, but the critical points of f are going to be the points in the domain where all partial derivatives vanish. So in other words, where the gradient vanishes or is equal to 0, or where the gradient does not exist. And then if the gradient does not exist, then that happens because one of the partial derivatives of f does not exist, right? So the general method that we follow is that we're going to find critical points using the first derivative test. So in other words, we're going to be using the gradient, and then we're going to classify those points we get. So we might get, like, I don't know, one critical point or two or three or something, maybe a whole circle's worth of critical points, and then we're going to classify the critical points using the second derivative test. And then we'll have to check the boundary of our domain, right? So as you can see from this example function that I've got right here, the maximum value of the function occurs over here. The local, when you go to check for critical points, you'll find there's this local maximum right there, and this local minimum here, and also a local minimum here, and I think this is one also over here. Then after you checked those four local minima, then you'll have to go along the boundary, because the boundary is where the actual maximum and minimum values occur for this particular function. So what we'll do for that is then we'll constrain to looking at what's going on a particular slice, and that corresponding slice looks like, oops, I think I went a little too far. There we go, right to there. And so then when we look at that slice, we'll be doing good old single variable first derivative and second derivative test, and we'll find, there's an extreme point here, critical point here and here and here, and then we'll check the boundary of this interval, which is just those 2 points, and so we look at the value of the function here and here, and now we've got all the information that we need in order to determine what the max and min are. So then the maximum is just going to be the largest value in this list, right? So we get a list of critical points, and here when I say max, I mean the absolute, I should say. So doing all this messing around with the function, we will have located, critical points, or points to check, points of interest, let's call them, this guy and this guy, and then these points on the boundary, and then these points in the interior. And if we evaluate the function at all of those points, then the one with the biggest value is going to have to be the max, and the one with the smallest value is going to have to be the min. And this function is sort of complicated, so I'm I'm not talking for the moment about, like, we would also have to check the boundary here, of course, and here, and we would, see things that we would want to have a look at. But I don't know. I chose this function because it's pretty, and it has examples of lots of different kinds of things like locals and globals, but it's also got about 20 points to try and check, and I'm not going to give you the one that's that complicated for homework.